Now, in the last lecture, we started calculating the velocity for uniform circular motion. We found that we needed to learn what the derivative of cos theta and sine theta, what these derivatives are. And I just showed you by drawing a picture that the derivative of cos theta with respect to theta is nothing but sine theta with a minus sign. The minus sign is because as you increase the angle, cosine decreases. Okay? And here I just put in omega t because I wrote sine theta before, but in my example, theta is just omega t. So I better write everything in terms of time, and I put sine omega t here. Is this clear? I'm just putting things together from the last lecture. And look at this here now. I didn't derive this one. Using the same picture, this is your homework to do for yourself, to get this kind of thing straight in your head, okay? But the answer is that the derivative of sine theta with respect to theta is cos omega t. And in each case, remember I have an omega here, which was just from d theta dt. Same omega here, so I've taken it out. Okay? Now, what is the speed? Which is the absolute value of this vector. The length of the velocity vector. Okay? Now, I have here omega r, which is just a number multiplying the whole vector. So the length is just omega r times the length of this vector. Remember the notation, this absolute value around the vector means the length of the vector, the magnitude of the vector. Okay? Now let us calculate the magnitude of this vector, minus sine omega t plus cos omega t. How do you calculate the magnitude of a vector with components vx, vy, or ax, ay, whatever? How do you calculate the length? Okay, let me give you an example. If my vector is 3i plus 4j, what is the length? How do you get that? 3 squared plus 4 squared is 25. Take the square root. Here, instead of 3, I have minus sine omega t. Instead of 4, I have cosine omega t. How do I calculate the length? Okay, so minus sine omega t squared plus cos omega t squared. That is the square of my length. So let me now do that. The result is the constant in front, omega r, times minus sine omega t squared plus cos omega t squared and take the square root of this. This is what length is. Okay? Well, sine square plus cos square is 1. Omega t does not matter. At any time, as the angle changes, the sine changes and the cos changes, of course. But this is very neat, very nice. Sine square plus cos square is 1. Okay? So the length of my vector is just omega r. And the vector itself, what was the vector itself? Is omega r times this I have just shown that this stuff in the square brackets, minus sine omega t I plus cos omega t j, has length 1. It is a vector, but it is a unit vector. Right? It is a unit vector for velocity. So I will write it, I will recognize this as unit vector, and I'll call it v hat. The unit vector giving the direction of velocity. So the velocity is, of course, any vector is just its length times its direction. Go so many steps in the direction of this vector. Okay? Well, I won't write it again. Okay. So I've just identified this as the unit vector in the direction of velocity. This is very simple stuff, but see what we have learned. By taking the derivative of the position vector, I have found the velocity vector. The absolute value, the magnitude of the velocity vector, I have found to be omega r. This I already knew before. Remember, I calculated what's the speed for uniform circular motion. Okay, if it goes 2 pi r in one period, in the last lecture we derived that the speed must be omega times r, physically. And here, of course, we find that. Speed is omega r. But as a bonus, we also find what is the direction. At any time t, what is the direction of the vector. Now I'll make a picture of the vector and I'll show you the direction. Okay? Here's my r vector. Here's my theta, which is increasing as omega t. And we just found that v equals speed omega r times direction, which was minus sine omega t I hat plus cos omega t j hat. Okay? And it turns out, first you see here that when omega t is like this, sine omega t is positive, minus sine omega t is negative. So the I component is to the left, x component is to the left, and the y component is positive, upwards. And if you calculate, if you make a picture, I won't do it here, and draw which angle is what, you will find that this is v. Here's your velocity vector. The length of the velocity vector is, the speed is omega r. The direction is tangent to the circle. How do I find that? Well, you can see that, let me just erase this for a moment. This angle is also omega t. So something with components minus sine omega t, and plus cos omega t, if this angle is omega t, plus cos omega t, is precisely in the direction of the tangent. The tangent has components minus sine plus cos omega t. Okay? So this time, by taking a derivative, I found the velocity vector algebraically, and then I went to my picture and looked for the angle or the vector whose x component is minus sine omega t, y component is plus cos omega t, and that is the tangent vector. Okay? And that's exactly what I expected, because here is the velocity. The velocity has magnitude omega r. I know that's the speed. And in what direction is it moving? Along the circle, in the tangent direction. Next moment, okay, here's my particle. It moves with omega t. Next moment, it's here. At this moment, its velocity was like that. When omega t comes over here, its velocity is here. It's always moving tangential to the circle, but it doesn't take off from the circle, because the next moment, when omega t is here, the tangent is now this. So, learning the derivative of sine and cosine and doing it with the derivative, finding the vector algebraically, I get exactly what I knew before for the speed and for the direction of this motion. Is this clear? So this angle is omega t, and the velocity vector is here, and this is v hat, its direction. Okay, so here is v, and here is the unit vector. This is v hat. Clear? V hat just says go in the tangential direction. And what is the speed? Omega r. That's the length of the vector. But the next moment, the vector becomes this. Okay? All right, now let's continue. I've got the velocity, and now I can calculate the acceleration. What is the acceleration as a vector? Well, it is the way the velocity changes with time, the rate of change, the derivative of the velocity with respect to time. Velocity is a vector. What does its derivative mean? It just means the x component and y components of velocity, you take their derivatives. Okay, so it's nothing but taking derivative of this thing. I have velocity already, so I have here omega r times minus d dt of sine omega t I plus the y component of velocity has a cos omega t here, so I take its derivative with respect to time. Okay? Any questions? Okay, now let's go on. The derivative derivative of sine, well, I put the minus sign already here. Derivative of sine is cos. Derivative of sine omega t with respect to theta or omega t is cos omega t. But now I have to multiply this with the derivative of omega t with respect to t. And what does that give me? Omega. Just as before. Derivative of cos omega t is what? With respect to omega t or with respect to theta is minus the derivative of cos omega t with respect to just the angle omega t is minus sine omega t. Okay? But then with respect to time, that gives me again an omega. And here is my j hat. Okay? Now in both terms, I have a minus omega. I can take it out. So now I have a acceleration equals minus omega square r cos omega t r plus sine omega t j. Does everybody understand how I got this? Yes? Because in doing the velocity, we learned how to take derivatives of sine and cosine. I just used it again. That's it. Now, we have found something, now that we know how to take derivatives, in just a few lines. And this something is very interesting. Now, let us think about what we have found. We have found that acceleration equals minus omega squared times this thing here, r cos omega t, I, r sine omega t, j. What is r cos omega t? Here is length r. R times cos theta, cos omega t is this. What is it? It's just x. It is just the position, x component. And r sine omega t is just the y component. Indeed, what I have here, if you go back 2 pages in our discussion, this stuff here is nothing but our position vector. So I have found that the acceleration in uniform circular motion is simply minus a constant omega square, the square of the angular speed, times the position vector. Now let me go back to the picture to see what this means. Okay. In fact, I'll make the picture here, but just to show you where to find things, I'll also do it first with sucrose. This is what you all see when you go to course for NS101, right? So please do that yourselves when you go home. This is just showing you circular motion. My particle is doing circular motion there. And of course, its x-coordinate is changing as cos omega t. So this is a graph of the x-coordinate. Positive, okay, and then becomes negative, etc. And this is the y-coordinate. That is showing you the whole situation as time goes on. This is the uniform circular motion. It's x-coordinate and it's y-coordinate. Okay? Now let me go to the next simulation. Here, this one shows these vectors. The black one in this picture is the position vector. As the particle moves around, of course, the position vector just points to the position of the particle all the time. The blue one is the velocity vector. It's always tangential to the circle, showing the direction of motion. Okay? And that means it's always perpendicular to the position. The position is this, and the velocity is perpendicular to it. And the purple vector is the acceleration in this picture. You see its direction is opposite, minus the direction of the position vector. Okay? So what does this say? The acceleration is always pulling towards the center of the circle. The position is away from the center to the point. The acceleration is towards the center. The velocity is tangential. Acceleration is the change of velocity. So velocity is like this, but at that moment, if this particle is going to move on a circle, its velocity as a vector must change, because if the velocity vector does not change, it moves on a straight line, right? Moving in a circle means, as a vector, the velocity is changing. The speed is not changing, but the direction of velocity is changing. And the change is the acceleration. How is it changing? Velocity is on the tangent. If it didn't change, it would move off on the tangent on a straight line. The change is to pull the velocity back towards the center of the circle. This is the acceleration. All the time the velocity is like this, acceleration is back to the center. So velocity becomes like this, but continues moving. Acceleration pulls it back towards the center. Okay? So the acceleration is towards the center, and we can understand that, but we have derived it mathematically. It's along the radius vector, but minus the radius vector towards the center. Is this clear? Okay. Now let me draw this circle again here. Okay. Here is position R, let's say velocity V, and acceleration. Okay? And our result is okay, the acceleration equals minus omega square times the velocity. Sorry, times the position. And I can write it as minus omega square r times the unit vector in the radius direction. So minus the unit vector means towards the center. This expression says my acceleration is directed in the direction of minus r hat. That means minus the radius direction. That means the direction pointing towards the center of the circle. And the magnitude of acceleration is omega squared times r. Okay? So the magnitude of A is simply omega square r. And let's remember that the speed was omega r. Okay, so we can also write the acceleration as speed square over r, v square over r. So we have learned quite a lot. But notice that this is not really physics. We have not asked yet why is there an acceleration. This is a later topic. We have only derived from geometry, from mathematics, the following. If something, for whatever reason, we don't know the reason yet, if something is moving on a circle with uniform speed, this must be accelerated, because acceleration means change of velocity vector. If the velocity vector didn't change, it will move on a straight line. Okay? So this is accelerated. If anything is moving in a circle, just the observation, the measurement that it's moving in a circle, tells you that it's being accelerated. And for uniform speed circular motion, the magnitude, the strength of the acceleration towards the center is v square over r. Okay. This is not a force. This is just an observation that moving in a circle means acceleration of exactly this magnitude. The acceleration must be speed square over r if the thing is moving and is going to move in a circle. If the acceleration is not v square over r, this thing will not be moving in a circle. Maybe to move on an ellipse or something else, but not in a circle. Okay? Clear? Any questions? Okay, this finishes our derivations of circular motion. Okay. Now I will make up some examples. Let's make an example together. Okay, Suppose you are driving. And you are driving your car, and you drive into a bend, a circular bend. Okay? Somebody give me a radius for this bend, for this turn. You are taking a circular turn in your car. Make up a radius. What do you propose? What kind of turn do you want? Pi over 3 meters. You are driving a car, pi over 3, this is about 1 meter. You want to turn 1 meter radius. Pick something larger. 20 meter radius, okay. Which is still sharp, but okay, let's say. Here is your circular turn and your little red car. Okay? And here our radius vector, radius magnitude is 20 meters. Okay. Now, you enter this curve with some speed on your car. Choose a speed. How fast do you want to drive into this turn? Somebody give me a speed. 60, okay, reasonable. V equals 60 kilometers per hour. Okay? Now, we can ask lots of questions. For example, the first thing we can calculate is omega equals what? Okay? What is omega? Omega is the angular speed. What's this meaning? When you enter the turn, here at this point, let's say you measure the position angle of your car from the beginning of the turn, you call this 0. So here it will be like 40 degrees or so, okay? So that's omega. How fast you go, how fast does this angle change, okay? Now what was omega? We already found omega. Omega is V over R. Okay, so it's 60, I want to make this into meters, so 60 meters. And how many seconds in an hour? 3.6 times 10 to the 3, 3,600. So this is V in meters per second. And our friend chose the radius to be 20 meters. Okay? So these cancel, this cancels that. This is a 3. This is a 1 over 1.2, which is about 0.8. Okay? So it's about roughly 0.8 radians per second. Roughly. Okay? Now, remember, a radian is about 57 degrees, something like that. Okay? So 0.8 radian is something like 50 degrees. So you enter this car at 60, this turn of 20 meters at 60 kilometers per hour. In 1 second, you are into the turn by about 40 degrees, quite fast. You're turning around. Okay? Now let us ask the period. What does that mean if you really have a full circular turn? Maybe you have a very complicated junction. You come from driving on this road, and there's a road in the same direction, but downstairs on the junction. So the turn takes you all around the circle, and you go like that, okay? Maybe. How long will it take you to take full circular turn? That's the period. Well, we remember the period is simply 2 pi over omega, because the full turn is 2 pi radians, and if you are doing omega radians per second, how many seconds will it take you? Okay? So it's roughly 2 pi over 0.8. It's about 7.5 seconds. Pretty fast. If you go on 60 kilometers, you make this 20-meter radius circle, and in about 7-8 seconds, you will have made the full turn. Okay? Now let us see how much acceleration you are putting on the car to do this. Okay, you are using your brakes and your gas pedal, you are doing things to the car to give it an acceleration. Let's find the acceleration. The magnitude of the acceleration is omega square r, or v square over r, whichever you want. But since we have already calculated omega and it's a simple number, let me use omega square over r. So omega square times r, which is 0.8 square times 20. Okay, which is about 12 meters per second square. Yes? No, this is a very good question. When you are moving on a turn, your speed in uniform motion is not changing. The speed is not changing, but the direction is changing. And to change the direction, you are steering the car. You are doing something to the car. That is acceleration. In uniform circular motion, the speed does not change. You are driving around at constant speed, but nevertheless, you keep changing direction. And you all know that when you're driving, you have to do something. Okay? That is acceleration. So even when the speed is constant, what you are doing is change the direction of the velocity. And that's quite a lot of acceleration. And the magnitude of that acceleration is, we are finding, it's actually about 30 meters per second square. Okay? In what direction? Towards the center of the band, of the circle. Okay? Now, is this a big acceleration? There is one acceleration that you have already used in your homework problems. That is gravity. Okay? What gives you your weight? What makes your car weigh 1 ton? Is gravity, downwards. Holds the car to the ground. Okay? That acceleration is 10 meters per second, 9.8, 10. Okay? So we are learning that to go a 20-meter circular band, if you enter it at 60 kilometers per hour, you are giving the car more than G. Quite a lot. Which is why, if you do this, you will feel the acceleration. You feel quite a big force. Okay? It's a lot of speed, 60 kilometers per hour. It's too much. And you can do it if you have a powerful engine and you want to show off. But this is crazy. Don't do it. 60 kilometers per hour on a 20-meter radius band is too much. So that's why it usually on a 20-meter band, before you enter, if there's a traffic sign, it says 30 or 20. It makes sense. You know, you stick your gear down, you brake. Before you enter, you are already down to 30 or 40 or whatever. Even 40 is a bit too much. Okay? So that after that, you don't brake. You go at constant speed, nicely turn around, and don't feel a lot of G. Okay? Let me make this correction. This is 12.8. Okay? Now let us use our fancy mathematics and write the vector position of this car. Let's say the car was here at t equals 0. We start looking at our watch or chronometer at the moment we enter the band. Okay? Then our car's position vector r is 20 times cos omega t. So cosine of 0.8 t, this is, remember, omega, in the x direction, plus sine 0.8 t in the y direction. These are the coordinates of your vector here. Okay? And here is your velocity vector. Now let me also calculate the velocity vector. The velocity vector is just the speed, which was 60, I'll give it in the usual units, 60 kilometers per hour. This is 20 meters. Times, we found that the x component of the velocity direction is minus sine omega t. So it's minus sine 0.8 t plus cos 0.8 t. Okay? And let me now write the acceleration over here. A, I know its magnitude. Okay? Its magnitude is 13 meters per second square, just omega square r. I put a minus the radius direction, which is and here's your acceleration when the car is over there. Any questions? Yeah, please.
Hocam arada kullanıyorum mesela. İçeri doğru dönüş yapıyoruz. Dışa savrulma var mı? Ben böyle hatırlamışım. Yani
Okay, good question.
Dışarı çıkmaz mıyız?
Okay, that is what you will feel, and we will learn about why later on. But that's, if you don't do something to the car, like give it an acceleration, turn the steering wheel, okay, to change the direction of your velocity, of course, the car would continue on a straight line. When you are moving actually on a circle, the free car direction, moving on a straight line, is, with respect to circular motion, outwards. The car's tendency, if you don't do something, is to move on a straight line. So that's what you feel when you say we feel ourselves forced outwards. You are not really forced outwards, but if you didn't turn the wheel, you would be moving on that line. But you are now doing this, so your body remembers that way. And we'll see why later on. We haven't learned that yet. Okay? But for some reason, if you actually make the car move on a circle, that means you have to give it an acceleration. Its velocity is not constant. Its speed is constant, same 60 kilometers per hour, but you keep changing direction, and that requires doing something. If you don't do anything, it will just keep going on a straight line. Okay? Any questions? Okay, let's see if I can make up another example. Or if you ask a question, we'll do that. Okay, let me give you an example having to do with vectors. Here's an example. Show that, let's say, we want to check really that R is perpendicular to V, or rather, V is perpendicular to R. We already showed that picture, you know, we found that its direction is on the tangent, etc. But let's now do it as an example to remind you of vectors. So we go 2 weeks back. Okay? Well, remember that we have 2 vectors, and we can get the information about the angle between them by taking their dot product. Right? Why? Because we showed that the dot product equals V times R times cosine of the angle between them. I'll call that alpha, not to get confused, okay? What is that? Well, this is V, this is R, and this is what I'm calling alpha. Okay? The angle between them. Or rather this one. This is alpha. Okay? At the same time, this is simply x component of velocity times x component of r, which is x, plus y component of velocity times the y component of r, which is just y. Okay? Now let us work this out. We have v times r times cosine alpha equals, let me write the v vector, omega r times, let me write it here. My v vector is just v. I don't need it as omega r now, minus sine omega t in the x direction, plus cos omega t in the j direction. I just found this. Okay? I know v as a vector. And my r is just the radius times cos omega t I plus sine omega t j. Now, I want here VR cos alpha is one way of calculating the dot product, but it must equal Vx times x plus Vy times y, which is simply VR times Vx. Okay, what is Vx? The x component of V is just V times minus sine omega t. And the x component of r is r times cos omega t. So the v and r I already wrote here. So I write here cos omega t. Now I do the same thing for the y components, plus, what is Vy? What is Vy? It's here. Cos omega t times, what is the y component of the position? I put the R already, sine omega t. Okay? So this gives me, this stuff here is 0. Well, that means cos alpha is 0. The angle between them is the angle whose cosine is 0. That tells me that it's perpendicular. Okay? Or 90 degrees. Any questions on this? So what you show with pictures always, of course, comes out of the algebra also. And I use that as just an example to remind you of how to use the dot product to check if two things are, what is the angle between them. Okay? Any questions on what we did here? So we have now finished circular motion. You have learned how to take the derivatives of sine and cosine. Of course, from now on, every time you have a derivative of sine, you don't have to prove it. As long as you learn how, you understand how it comes from the concept of taking derivative, okay? That's it. Now you know how to take derivatives of lots of things, how to take integrals, and you know this about sine and cosine. And now we are really ready to start next lecture, Newton's laws of motion. Okay? Any questions?